Hi, this is APES, Chapter 18, Section 3, and Chapter 18, Section 4. So for our objectives today, we're going to be looking at acid deposition. Okay, so again, main cause of acid deposition is in our objective here, coal burning power plants, motor vehicle emissions, and sadly in some areas it does threaten human health, aquatic life and ecosystems, forests, and human-built structures. Okay, and there we go. So what is it exactly? All right. Well, here's the thing. Acid deposition that is caused by being downwind of coal burning facilities and urban areas with lots and lots of cars. There's wet deposition, where we can talk about rain, snow, fog, cloud cover with a pH of below 5.6. Let's do a quick thing here about acids versus bases. Quick and dirty, acids tend to give up hydrogen ions. Bases tend to accept hydrogen ions. That's one definition of an acid base. And that's where I'm going to stay with it. Okay? When we look at pH, that's a scale. Typically goes from 1 to 14, depending. It can go to 15, but the idea is this. On a 1 to 7, on a 1 to 6, the pH is an acid. Okay, it's a logarithmic expression of concentration of hydrogen ions. The lower the pH, the more hydrogen ions you have, which means the more concentrated the acid is. It is not the strength of an acid. Okay, on the other side of the coin, pH is 7, it's neutral. Basically, think water. And then from a pH of 8 to 14, it becomes more of a base, basic, meaning that as you go up the pH, you have less and less concentration of the hydrogen ions that are there. So that's a quick review for the pH scale for those of you who may not have remembered it. Okay. So a wet deposition, rain, snow, fog, cloud cover with a pH of less than 5.6. Now, typically this happens anywhere from 4 to 14 days far away from the sources, but it's downwind. So we have a couple of examples of that. In Ohio, yes, the great state of Colby, Ohio, okay, SO2, sulfur dioxide emissions, they do suffer from the effects of acid rain. Acid rain. When the trees go brown, you know it's bad. Acid rain. When the buildings start going down. Acid rain. Okay, we'll move on. Now, and mention to you about acid fog in Southern California. Okay, treetops in LA, area high up in the mountains have a fog with a pH of 2.3. It's an extreme, but that does happen. And again, this is a problem. You know, we have a lot of cars in LA. We do give up a lot of pollutants. But again, your number one source for acid deposition like this, it's burning coal. You're getting SO2 emissions from there. And we move on. Now, there are other forms of acid rain in there. Now, in dry deposition, the particles fall. Okay, so a bit different. You're not mixing it with water. It's just pretty much the flakes fall on you. That happens to 2 to 3 days fairly near the source areas. Okay, now, of course, when you're talking about acids and bases, there is something called a buffer. Now, the idea behind a buffer in acid-base chemistry, it makes it hard for the pH to change. So, for example, if you were, I would do an experiment with AP Bio when I taught it, was you had 1 cup of water, 1 cup of water with a buffer in it. And what you would do, you would measure the pH of both cups of water, the water and the buffered water, And then you would start adding drops of acid to it. Could be vinegar, could be hydrochloric acid, doesn't matter. And what you found was that the non-buffered water, the pH went down faster, okay? It went down very quickly. So in other words, that water became more acidic because of that. The buffered water, air quotes, the buffered water, on the other hand, it was much more resistant to changing the pH, to lowering the pH. Well, how come? Well, the idea about a buffer, it helps resist the change. Why? It absorbs the acid. It reacts with the acid and cancels it out. But a buffer also has a limit that if you keep adding the acid to it, eventually the buffer will go away. Okay? That's just the way it is. Now, so what kind of buffer were you talking about in your little experiment that I did? Actually, a little bit of baking soda, not much, just poquito. And it worked out very well. Sorry, guys, that would have been a great one to do with you guys as a quick thing, but all right, so buffer. So some areas have something called limestone or calcium carbonate, CaCO3. This acts as a buffer. Limestone has been used many times in the past for different things, like cement, for example. They've also used that to treat lakes that are a little more acidic. It does reduce the effects of the acid deposition. Now, you don't have to worry about how it reduces it. Just understand that when you've got a buffer there, it makes it very hard to change the pH. So you've got it. What is acid deposition and why is it such a problem? Well, there's a couple of ways to look at the acid deposition. There's SO2 and then the NOx. You also have O3 that comes in and plays its role in there. So there's a couple of things. This diagram really does a great job of explaining it. So first off, let's look at our emission source here. We have our factory putting out smoke, and whatnot, probably burning coal. So you got SO2, you got your NOx. Now remember, the NOx, it could be NO2, could be NO3, could be NO. No! Say it ain't so! Okay. So when they're up in the air, there's a couple of places they can go. One, they can go directly into dry deposition and not that far away. So that will fall in dry deposition of gases, particles, and aerosols, and that will fall in the plant life. Or through the process of oxidation with O3 combining with water up there in the air, you end up getting H2SO4, which you know that as sulfuric acid. And then you have HNO3, which you also know as nitric acid. So what's happening? What's going on? Well, if you break it up, you end up getting 2H plus SO4 with a -2. Okay, and then you have H plus NO3. Now remember, those hydrogen ions, there's your acid. Okay, so you got wet deposition for H plus NH4 plus, because you know what? You get ammonia coming from the ground naturally. That also reacts with the hydrogen ion in the atmosphere to form ammonium. Okay, and that also is part of the wet deposition. Okay, so there's some aspects that are normal, like the ammonia. The not normal, the abnormal, is having the SO2 and NOx combine to form sulfuric acid and nitric acid, and then they fall. And then that's where you end up having the wet deposition of dissolved acids. That's where the damage is happening. Okay? So what are the consequences? It makes people who suffer from bronchitis and asthma even worse. It's awful. Now, it also leaches toxic metals like lead and copper from pipes into the local drinking water under the ground. Well, wait, what do you mean by leach? Think of leach as washing away. Okay? That's what leaching is. It's washing away, it's dissolving the lead and the copper from the lead and copper pipe. It comes in contact with the surface. It takes away some of the lead ions, some of the copper ions. It goes into the ground and then it affects the drinking water. That be a problem, yo. So it damages statues, buildings, and national monuments. Well, right, because a lot of those statues, buildings, and national monuments are made up of marble, which is a kind of limestone. So when the acid rain hits that marble slash limestone, there's a natural reaction. It starts to dissolve, it starts to break down. So now you guys can start seeing where the damage is happening with this. Now, the other side of the coin is fish are also affected by the pH of less than 4.5. It kills them, not just because of the acid, but you can also have aluminum leaching out of compounds into the water, and then it's not good for the fishy. Wow, who would have known all this? Okay, so what other consequences do we have? I've mentioned 4. Now let's look at the 5th, acid shock. Imagine you're getting a sudden runoff. So you got this accumulation of water on the ground with the acid, and now because of this amount, now it's going into the lake. So now the pH of the lake isn't going to go up because that's not basic. It's going to go down, making the lake more acidic. So that gets to be a problem. Okay. So example, Norway and Sweden. Now, they're very high up. I mean, they're kind of close to Santa's workshop there at the North Pole. They have lots of lakes there, lots of snow. Okay. But there are a number of lakes there that don't have fish in them because they are virtually unlivable for the fish. Okay. If you were to go and take a swim in that kind of lake water, you are going to feel it on your skin very quickly. Okay. It's going to burn and it's going to hurt. No, you're not catching on fire, but it will burn. So that's Norway and Sweden. Canada, on the other hand, Canada has lots of lakes also because it is closer to Santa's workshop at the North Pole than the rest of us, okay? But they have very few, if any, fish. So they're running into the same problem that Norway and Sweden have, that acid deposition lowers the pH of the lakes and then it causes the fish not to survive very well. Now, animals, from a biology perspective, there is that range of tolerance, and we have talked about that earlier in the year in the first semester. There is that range of tolerance. If the pH level is too low, the animals are going to suffer. The fish would suffer, okay? If there's too much acid, the fish are more likely to die. Very few fish would be successful at surviving, let alone reproducing. Okay. How about the effects on soil, the dirt, depleting nutrients? Okay, as the acid hits the soil, it's going to mix with compounds in the soil and take those away, the compounds that plants need in order to grow and be successful. Oop. Now, what about acid rain or acid deposition, if you will, hitting plants? Is there an effect? Take a look at the picture on the right. These are leaves from the same kind of tree. The one on the top is a normal, happy leaf, nature's own solar panel, right? Because it does that, takes the sunlight in, gets some action going, and you get some photosynthesis. Great. If you look at the leaf on the bottom, you notice, what happened? Well, what do you mean? Oh, there's like a lot of holes in there. Yeah. Did they run in a cooter and scooter them shotguns? No, no. What you're seeing there, those holes are caused by acid deposition. Oh, it wasn't Cooter and Scooter? No, no. That's what happens with acid deposition. It will literally punch holes in the leaves. Okay, and that does damage them and it does weaken them. Okay, so pay attention to those things. All right, so hang on. What else? So, how can we handle that? Well, one way we can help the plants is actually adding extra nitrogen in there. We can do that with fertilizer. We can add that in there in the form of ammonia. And at first that's cool, but what happens when you have too much of a good thing? It goes bad. So that's a problem. Now, synergistic. Synergistic means, think about this. You're taking two things, all right, and they work together. They are individuals. They do things when they're individuals, right? But if they combine, now with that synergistic interaction, they are more powerful, like max power. Okay? Or if you're familiar with Marvel movies, you remember that dude played by Carl Urban. He had those two rifles, Des and Troyer. By themselves, they're deadly. Combine them, you have Destroyer. Synergy. So what happens? Synergistic action. Sulfur dioxide and ozone combine in large amounts. Okay, what does that do to the plants? It damages them a lot. That's why I'm saying deep hurting to plant life. Really brutal stuff. Okay, so what can we do? Well, reducing or eliminating the sources, your SO2s, your NO2s, your NOxs, and particulates. Instead of burning coal, we could use wind turbines or natural gas for the energy, burns more cleanly. Yeah, that's true. Large amounts of lime or limestone can neutralize lakes and soil. The problem about that is it does get expensive, and you have to do it every year in order to counteract the effects of the acid. So what you're doing, if you got a pH of 4 and you want to bring it up to a pH of 6, you've got to add some limestone in there to bring that balance back up. The problem gets to be that's not a forever solution. That is a temporary solution. Okay? You still have to deal with the problem. The best way is to reduce or eliminate your sources. Okay? Now, there are air pollution laws that have also helped reduce acid deposition. Now, when you take a look at these two pictures here, this would be an example of a statue before. It's the same place, same statue. Look at the statue on the right. That's the same one. That's the effects of acid deposition, because that statue was made of marble. Oops. Or, in other words, don't! And that statue doesn't get to come back, boys and girls. It doesn't happen that way. Okay. I think we're going to be done here for our time. So 18.3, we talked about acid deposition. We looked at what is it a problem, what are some of the solutions that we have here. We know that it does damage to the soil, it does damage to fish, it does damage to lakes, it does damage to plants. We looked at the impact it has on human beings, okay, affecting our drinking water, increasing respiratory diseases like asthma and bronchitis. We know it damages buildings. We know that. We know what's happening in the atmosphere. We know sources like SO2 and NOx, they go in with O3 helping the oxidation process. We get sulfuric acid and nitric acid. And then combining with water, falls, hits the ground, and causes damage that way. Okay, we talked about the idea of buffers. We looked at dry deposition. Okay, that's where particles fall. This is not the same as acid rain. Okay, when we look at wet deposition, then we can sit there and talk about acid rain. And don't get me to sing that again. Okay, We looked at examples of where this is really happening, including Southern California. Guys, there are other places that the acid rain has been an issue, especially in Europe and some parts of Germany. And again, we didn't know any better. This is something that took time to happen. Okay, and with that, guys, I am stopping here. Hey, I'll catch you on the 8-4, 18-4, guys.